As Sam said, my name is Gonzalo and I'm a DPhil student in mathematics. And I'm working on the numerical modeling of glacial sliding. So I think you all have an idea now of what I mean by glacial sliding, and I'll try to also convey what numerical modeling means as well. So just a few short words on glacier modeling in general. When we talk about modeling, we talk about a set of equations, the model, which we can use to describe the dynamics of a glacier. And we're usually interested in models because they help us understand, in general, the behavior of ice glaciers and to make predictions. And I think when we talk about predictions, what comes to mind for all of us is sea level rise. And these are just some figures from a very recent paper where the authors carried out simulations in order to predict what kind of sea level rise we can expect from the Antarctic ice sheet under different sort of carbon emission situations. Now, more particular, a fundamental component of this glacier modeling, as Tom also really emphasized in his talk, is glacier sliding. And from a modeling perspective, what's really happening here is the following. If you think of an ice sheet or a glacier, you have a mass of ice that is probably over 100 meters thick, right? And in a very thin layer close to the bedrock that you can expect to be, say, for example, of 1 meter deep, you have this multitude of physical processes occurring. No? So Tom, for example, showed us these images of ice over till. You can also think of ice over a hard bed cavitating with water-filled cavities. And the fact is that these processes, due to the difference in length scale, cannot be captured by a model. I mean, it's just virtually impossible. It's computationally impossible to just sort of accumulate all of this inside a model. So what we do is we sort of simplify the bedrock and assume that there's a relationship between the speed at which the glacier is sliding, this variable which I call U sub B, and the shear stress and drag exerted by the ice onto the bed. And this relationship is what we call the friction law. And the friction law is a fundamental component of any sort of model of a glacier. And just to show the importance, we can have many different mechanisms occurring at the bedrock. So for example, here in this sort of zoomed in image of this layer in between the ice and bedrock, we see two fundamentally different mechanisms. No, ice sliding over till, over this sort of sediment that deforms, and ice sliding over a hard bed. And the fact is that these different mechanisms lead to different sliding laws. And what I want to emphasize with this is that different sliding laws lead to different predictions. So again, another paper, recent paper on sea level rise, showing the sort of probability distribution of what we can expect the sea level equivalent mass loss to be by 2100 from the Antarctic ice sheet. And what we see is basically that we get quite different predictions with different sliding laws. So all of this emphasizes the importance of understanding glacial sliding. And if we think about how we can try to understand glacial sliding, well, here I just give a sort of classification of approaches that I came up with. If we think about empirical approaches, if there's even such a distinction, right? Already Tom showed that you can also use a combination of theory and observation to also try to understand these sliding laws. But just for the sake of the discussion, if we think of empirical approaches, one could try to get field measurements, and that's extremely difficult. And to my knowledge, the only example I can think of, which I learned about recently, is this subglacial observatory, which is this image on the left. And this is a cavity in the Argentière Glacier in the Mont Blanc Massif in the French Alps, which researchers realized was accessible in the late 90s. So if you step inside this cavity and you look at the roof, which is basically the base of the glacier, you can actually see it sliding. There's a very cool stop motion video on YouTube where they show this sliding. And they installed a bicycle wheel in contact with the glacier. And through the rotation of this wheel, they actually have measurements of sliding velocities. But this is extremely rare, and we cannot count on these sort of events, I would say. There's also laboratory experiments. So this is an image of a machine that was built by a research group at the University of Idaho, where using the rotation of a plate attached to ice, they start making ice slide over a bedrock, and they can actually get very precise measurements of the basal drag and the sliding speed, and actually reconstruct sliding laws. Interestingly, they actually reconstruct sliding laws that we can obtain with theoretical methods. So it's quite a nice sanity check in that sense. But anyways, I'm working on purely theoretical approaches, and that means I'm using mathematical models. And in particular, I'm focusing on hard bed, sliding over hard beds with cavitation. So again, the image I showed before of the sort of different mechanisms that can cause glacial sliding, I focus on this sort of regime on the left, where we assume the bedrock is a solid, undeformable body. And this process called cavitation occurs. So cavitation is the detachment of the ice from the bedrock. Usually cavities are filled with water. In fact, we can usually expect a thin layer of water to exist between ice and bedrock. And it's very interesting because as soon as we have cavitation, we're already linking sliding with the hydrological system. So the hydrological system, which Michael talked about on Monday, and unfortunately I couldn't attend the talk, is also a topic that's widely studied now. And it's precisely through this hydrological system, through all these conduits of water that infiltrate the glacier and reach its bed, that we find very interesting relationships between water pressure and sliding. And that's something I will also show in a few slides. But anyway, going back to sliding over hard beds with cavitation, if we want to model, we can set a series of equations that could describe this process. So you can imagine that we have equations for the evolution of the ice as a viscous flow. We have an equation to describe the change of the cavity shape. And then we have a series of contact conditions, very specific type of boundary condition between ice and bedrock that allows us to model this process of detachment. And the fact is that the sort of overall mathematical system of equations is a very complicated one, very, very delicate, with a very interesting mathematical structure. And in the past, different researchers, in particular Andrew Fowler, who was here in Oxford, and his student Christian Schuh from the University of British Columbia, they found the method for solving this system of equations by simplifying, linearizing, and actually being able to arrive at an analytical solution. So that's what I call solve by hand. But this comes at the cost of simplification. And the fact is that we can avoid such a simplification if instead of solving this by hand, as I just said, we actually solve it numerically. And this has only been done once. So this is precisely what I'm doing, because we think that the way it was done in 2007 by Olivier Gagliardini might not be the best way. And well, I'm in contact with Olivier. He's great, and he's helping us a lot. But that's precisely sort of what I've been doing. And I just want to say a few words about what I mean by numerical modeling, in case there are people in the audience that aren't familiar with this term. So numerical modeling, or numerical analysis, which is sort of the name given to the field in mathematics, is really the construction of the transformation of a system of differential equations, which establish a series of relationships between physical variables. Say, in this case, we have the cavity shape, we have the ice velocity, the ice pressure. And this system of equations can be transformed into a finite number of calculations that give us a finite quantity of, a finite number of numerical values that tell us something about what this pressure, velocity, and cavity shape should look like. You're essentially approximating the sort of ideal solutions, the velocity, the pressure, and the cavity shape, which are in a way inaccessible because you cannot solve the system of equations by hand. But using an algorithm, you can find approximations basically by just crunching numbers in a way. But I think the beauty of numerical analysis, and I think what makes it a sort of art in a way, is the fact that there's an infinite number of ways of transforming a differential equation into a finite number of calculations. And each of these approaches has advantages and disadvantages. And with insight into the sort of structure of this differential equation, you can build algorithms that, well, as I say here, preserve certain fundamental properties of the physical system. And these leads to very robust and stable numerical methods. And really, my whole project, most of my project has been exploring this numerical modeling of basal sliding with cavitation from quite a mathematical point of view. And we now have an algorithm that is quite robust and stable. Still improvable, but it does the job. And I can show some results from this numerical modeling of basal sliding with cavitation. So this is an example of some computations. And what we have here is 3 different situations with different water pressures. So these 3 figures would sort of be a zoomed in image of what's happening when the glacier is sliding over an undulating bedrock. And what you see is that when we increase the water pressure in the cavity, the ice cavitates more and more. And it's this process of cavitation, these calculations, that allow us to reconstruct a sliding curve, taking into account a varying water pressure in the cavity. And these are very well-known results. So this kind of sliding curve has been obtained in the past, so this is nothing new. And what we're actually looking at now is what happens if the water pressure is actually varying. What happens if we have an oscillating water pressure? And it's interesting because there have already been several publications that, with field measurements, have explored the relationship between water pressure at the base of the glacier, which you can measure by digging a borehole into the glacier, and with a pressure transducer you can obtain water pressure measurements, and you can relate that to surface velocity measurements with GPS. And this is something we're exploring at the moment. I didn't show results just because I thought it would be maybe overcomplicating the talk a little bit, but that's one of the current projects we're looking at. So here is in particular just some more images from one of these publications where you see that they measure the water pressure at these boreholes along this alpine glacier, and then they obtain these measurements that relate the water pressure oscillations in the time scale of days with increases and decreases of surface speeds along the glacier. So these sort of situations we can simulate in a very, very idealized context. And it's interesting that we obtain results that qualitatively look quite similar in certain ways. Obviously, you have to take it with a pinch of salt since we're simulating extremely idealized bedrocks. But anyways, it's interesting. And to finish the talk, I would also like to say that one of the reasons that we've spent so much time on understanding the mathematical structure of this problem of subglacial cavitation is because from a purely mathematical point of view, this mathematical equation that you get when you're modeling a detachment process, it's what we call a contact problem, is actually the same sort of problem that arises when you're modeling a marine ice sheet, that is an ice that slides over the continent into the ocean. And you have this grounding line down here, which is a sort of point where ocean, ice, and bedrock meet. And modeling the evolution of this grounding line is essentially a contact problem, which our algorithm can also tackle, let's say. So that has also been one of the main reasons why we've dedicated so much effort to trying to get the maths right behind these sort of contact problems, because eventually we also want to step into these grounding line problems of marine ice sheets. And that's pretty much it. Thank you very much for listening, and please feel free to ask any sort of question. I'd be happy to try and answer it.
Wonderful. Thanks, Gonzalo, for a great talk and a really cool insight into what you do. Again, same thing, just stick your hand up if you've got a question, drop a question in the chat, or just unmute yourself and go ahead.
So I think Tilly has a question. I'm seeing. Oh no, that's not a question. Sorry, Tilly, that was
clapping
applause.
hands.
Clapping.
Okay. Well, I can get us started. I'm curious about what you were saying to do with the way that models, of course, they can't resolve these small scales that Tom showed us in that amazing picture, for instance, with the till and that big sort of boulder in the till and all the complexity that you get with these different contact points and the cavities, etc. But you're doing quite idealized modeling, which enables you to interrogate kind of smaller scales, right? I just wondered if you could give us a sense of what the difference between what you're doing and the scales that you're working on with, let's say, the model that is it DeConto shows in that 2021 paper, or uses to predict sea level rise. You know, these are very different scales of modeling, right? Modeling on an Antarctic wide scale in order to get sea level projections versus doing idealized sort of process modeling on these smaller scales. And is the ultimate goal that this smaller scale interrogation will help to improve those bigger models?
That's a very good question. And honestly, it's a question that I ask myself a lot as well. I think part of this PhD is an exploration of to what extent such idealized models can actually give us practical information. And at this point, I've seen that using such idealized models can answer very particular questions. So it's quite interesting that, for example, something that we've observed already is that if we have an oscillating water pressure, which is quite a reasonable situation that can occur, we already see that certain points of the sliding curve, certain points of the curve sort of become unstable. That is, if you're perturbing the cavity tends to fall always to a certain part. So already that has allowed us to, for example, speculate about the fact that certain sliding curves that have been proposed theoretically might be physically implausible because the cavities tend to have certain stabilities that don't allow them to cavitate as much as the theory kind of shows it could. So that's sort of what comes to mind as an example of the kind of answers that such specific idealized studies can give. But it's true that when it comes to modeling a large scale glacier, it doesn't seem that such an idealized treatment can really give you a friction law. I'm not sure if that answers your question.
Yeah, thanks, Gonzalo. No, that is helpful. Just another quick follow-up. So what is the smallest scale that you resolve in these idealized models, or is it kind of dimensionless?
So it's dimensionless, and I think it's more like, I think the better question to ask from a numerical point of view would be, what is the sort of spectrum of scales that I can resolve in one simulation? Because imagine that, I have a sort of predominating larger scale bump, but perhaps we could also superimpose smaller scale bumps. If you do that, the computation will become extremely difficult because you have to have a sort of mesh refinement around the smaller bumps, and that will probably become impractical. So I think these sort of such detailed numerical computations are limited to solving over one particular length scale of obstacles, right? So, and that's more the question, right? Like, how many length scales can you superimpose? And the answer is that not too many, really.
And there's no scale similarity, or is there? Like in sea ice, for instance, we see that there's a lot of similarity on the large scale deformational features as to the smaller scale. So I just wondered if that's anything that pops up in glacier sliding. But because if you have these different scales superimposed, then you know, maybe there is some similarity between those different scales, but I really don't know anything about this, so don't take my word for it.
Well, I mean, no, it's. I'm not sure if it's related to what you're asking, but it is true that, for example, if we would have sort of two length scales superimposed, two length scales of bump amplitudes, as soon as you have cavitation, you'll probably sink the smaller bumps, since cavitation will probably occur on a sort of dominating length scale. So it seems like there might just be one particular length scale that sort of dominates the process of cavitation, and hence the calculation of these basal shears.
Okay, thanks. Yeah, that's interesting. We've got a couple of questions in the chat, so I'll just invite Michael firstly to unmute if you want to, Michael.
Hi, thanks, Gonzalo. I was just wondering if you could mention why, or what you think went wrong with Gagliardini's approach. Was it something that they did mathematically, or was it more in the numerical method, and therefore do you expect your findings to be different from theirs? Or are you just figuring out a better way of doing the same, like what they did?
So it's actually very interesting and very complicated, all of it. Like, I'm at a moment where I'm talking a lot with Olivier right now, and yeah, things are interesting and complicated. So on the one hand, the motivation that led Ian and I to start looking into his problem is that the 2007 paper, the sort of results they obtained hinted at a sort of general sliding curve for different parameters, and their numerical results were extremely noisy, just all over the place, and they really seemed like something was going wrong there. Now, the way Olivier Gagliardini and his group talked about this contact problem in cavitation sort of ignored the fact that from a mathematical point of view, it can be expressed in a very compact way. So a partial differential equation with contact boundary conditions is essentially a variational inequality. And that's a very particular mathematical structure that can be solved numerically in very interesting ways. And they seem to completely ignore that. So I think those 2 points motivated us to step into it and try to do it in a way that preserves those physical, those mathematical structures. And we did it, and our results do look much better than the 2007 results, and they already show that some of the speculations that those results led to were wrong. Okay, so that's the sort of outcome. And now the interesting thing is that I've been in contact with Olivier, and 13 years later, he's obviously improved his algorithm. And the fact is that now he gets very good results. So I am starting to wonder, and he does ignore the mathematical structure. So yeah, I'm at a point where I'm also questioning, like, sometimes it seems like mathematical rigor is not that necessary. I don't know. I'm still exploring that. But definitely with respect to 2007 results, it did hint that something was going on wrong. So that was the prime motivation. It is like, yeah, it is. I am at a bit of a moment of crisis.
Thanks. Tom's got a question.
Yeah. Sorry, I was just getting carried with that. Yeah, I guess my question is, I really like simple models, because simple models are easier to understand, right? So I really like your modeling approach. I guess my question is, in real systems like the systems we observe, I think the bed is often, there's often soft bed, maybe in conjunction with hard bed. So what additional complexity would arise by you introducing a soft bed into this cavity problem? Or alternatively, could you, other ways of sort of creating a hard bed cavity problem that sort of simulates or is a proxy for a soft bed, or at least a bed that is much more complicated, but only explained by a simple bed? That makes sense.
That's a very good question. So for your first part of the question, which I understand to be, in what sort of way could we integrate also the effect of a soft till existing over this undulating bed? And I think that can easily be included in the model as follows. So the way I'm doing it now, I'm assuming perfect sliding over bedrock and ice. between bedrock and ice, sorry. And that means that one of the boundary conditions that I enforce is that the tangential shear stress of the ice onto the bedrock is 0. However, we could also enforce what we call a Coulomb friction. So a Coulomb friction might be the adequate way to model till, since it's got this sort of a characteristic of like sudden failure and sliding. So that's very easily integrated into the model, a Coulomb friction. And so Olivier has actually recently done some computations with that, and it doesn't change the sliding curve very much. And then for the second question, could we represent sliding with till with sliding with cavitation in a way? Is that what you were sort of asking? Because I think what I've seen is that I recently remember reading this paper in Nature, or I don't know if it was Science or Nature, where they talked about the existence of a universal slip law, which is essentially like a sort of regularized Coulomb law. And I think the finding is that if you look at both sliding over weak till and sliding with cavitation, both of them lead to a very similar sliding laws. So somehow the outcome is very similar. So perhaps, is that what you were hinting towards with what you said?
Yeah, exactly. Yeah. Like, I guess I think of your problem in a way, maybe incorrectly, as it's kind of almost dictated to some extent by the ratio of the, you're talking about having lots of small cavities versus a few big ones, and that kind of dictates a ratio between, I guess, the fluid involvement and then the kind of topography involvement or the hard bed. But I guess you could vary that ratio and it might simulate a more complex bed without you realizing it. Well,
exactly, yeah.
Yeah, I don't know. Anyway, thanks for the talk. It's very interesting.
Thanks.
Great. Well, we are now at 2 p.m, so it's probably best that we wrap up. But I'd like to thank everyone for coming to listen, and also to our 2 speakers for 2 awesome talks. There is a question in the chat that we didn't manage to get to. Maybe Tom or Gonzalo, you can have a quick look, and if it piques your interest, you can get in touch with the EPE directly if you think it's something you could pick up. But yes, thank you everyone for coming, and hope you'll join us again tomorrow. And thanks again to the speakers. Cheers.